This one, obviously, if you take that same table here, you can get the same thing twice. So there's going to be 9 outcomes here, right? Because you can get 3 things on the first pick, 3 things on the second pick, so it's going to be 9. If you look at what they are, okay, it's all those same outcomes there before. If you count the outcomes here, when you have this all done, and could have made this a bit bigger, I guess. This one down here black, then the second white one, and then the black one, then the black one again. If you count the outcomes here, there are 9 outcomes altogether, obviously. And the ones you're looking for here, if you're looking at what's the chance of getting white on both picks, it's these ones, right? There's white on both picks, those 4 right there. 4 out of 9. That's what the probability should be when we work it out. If we look for a shortcut here, shortcut's going to be the same as what you have, looked at before, multiplying. Okay, but it's important to see that that comes from just writing out the sample space as well. The chance of A happening, probability of A is still 2/3, but now it isn't that it disappears; it's put back in there now. So what's the chance of B happening? And does it matter here? Chance of B given that A has happened, what's that? 2 out of 3. What's the chance of B given that A has not happened? Does that matter in this case? This is 2/3 as well, right? Doesn't matter what you got on the first pick. Contrary to what people believe, some people believe that if you get the white one on the first pick, you got a better chance of getting the black one on the second pick. Or if they think if you got the black one, then you got to, like when you're rolling a dice, if you think, well, I got 6, I rolled a 6 3 times in a row. What's the chance of getting 6 this time? Well, it's really low. These are independent. Each pick is independent. Doesn't matter what you get on the previous pick. This is the same number here. This is the same as this. You can actually just call it probability of B then, if it isn't affected by event A, right? You don't have to put that condition on there if the condition doesn't matter. Probability of B given that the first ball is white, right? Probability of B given A, or just probability of B because that condition doesn't matter is 2/3. 2/3, that's where your 4/9 comes from. This is just probability of A times probability of B. You don't even need to put the condition on there. 2/3 times 2/3 is your 4/9. So that's the shortcut. These are independent events for reasons that I think you realize already. Just in everyday terms, because what happens first does not affect what happens second, right? The probability of B happening is not affected by knowing whether A has happened or not. Or if you want to say it mathematically, chance of B given that A happens is the same as chance of B given that A does not happen. Those are the same. Knowing whether that's happened or not doesn't change the probability. So those are the same, right? This is 2/3, this is 2/3. All right? Any questions about that? We can put it into more formal terms down here on this page. Okay, what some people call this multiplication law. You can multiply 2 probabilities. You already know that AND is going to somehow deal with multiplying things. You can multiply these 2 probabilities. If you want to know the probability of A and B, you can take probability of A, multiply it by probability of B. It's just that you need to add that condition on there under the condition that A has happened. When you learn this in grade 8, sometimes grade 8 say, well, how do I know whether, which one you got first? Well, we would always say to grade 8s, well, if you're looking to get A and B, it's not going to work unless you get A first. So just assume that you got that A happened when you're figuring out the probability of B. That's all you're doing here. You're not doing anything more complicated. Just you're using this notation, A given B. Now, just like any other formula, you can rearrange it here. Right? You can take this if you have. I know that this is tough sometimes because you're using this to represent a single number. Right? It was tough in grade 7 or 8 when you learned that X could represent a number, a single letter. Then you became okay with that. Now look how many things you're using to represent a single number. Right? All that means one number. Probability of A and B. You can rearrange that formula just like any other formula. X equals Y times Z. You can put this down below here, right? If you want the Z by itself, you can put that underneath there and isolate it. So you can do the same with this formula, right? Probability of A and B equals probability of A times probability of B given A. If you want to rearrange this, if you want to know that conditional probability, you could divide two other probabilities here. You could do that division, right? That's all that formula says there. All right? Okay, thanks. All right, so either way you use this way or this way, it becomes useful for you here. Now, I don't want you to think this is the only way you can do these kinds of questions or something. It's just another tool that you have to use to work with probability. There's the special case of this is when they are independent events. It's not anything different. It's just when that condition doesn't change the probability of B. Then the rule simplifies to A times B. Probability of A times B. Here's a really earth-shattering statement. Two events that are not independent are called dependent. Don't confuse this with mutually exclusive or not. Remember the last time we talked about mutually exclusive or not? Mutually exclusive means if one happens, the other cannot happen. That's not what we're talking about here, right? Up here, okay, so go back to, if that's okay, go back to this. In either case here, this event and this event, are they mutually exclusive or not? Mutually exclusive means can they both occur? If you get a white one first, does that mean you're not able to get the white one second? No, you can still get a white one second. The chances are different, but it can still happen. These are not mutually exclusive because they can both happen together, right? If you put all the outcomes where A happens and all the outcomes where B happens, there's an overlap, right? Where you can get a white one both. It's a couple of them there, right? Otherwise, the probability would be 0. This one, they're not. This one, these two events are. It's the same thing here, right? They can both happen. Whereas on the first one here, are the events not A and not B? Are they mutually exclusive? As in, if you get the black one, if you get the black one first, what does that mean about this event here? If you get the black one first, can you get the black one second? No, you can't, right? Those are mutually exclusive. If you know that you got the black one first, you cannot get it second. Like they can't occur together. They're dependent, but they're mutually exclusive. If this one occurs, this one can't occur, and vice versa. If you know you're going to get the black one second, then you can't get the black one first. If you know that's going to happen, this is not going to happen, right? Anyways, there's some problems to look at in here that you can work on. If we're going to solve some of these, I don't want you to write out all the whole sample space for this. Obviously, there's 52 cards. If you made a table for this, you don't want to list all the cards here and all the cards here you could get, right? That would be a pretty big table. How many things would there be in your table? How many outcomes? Think about if you're drawing 2 cards here. Actually, I should stop this and start again.